Hello, guys. I hope you are okay, are bearing as 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 best as possible this weird situation we have ahead, this coronavirus situation. I hope your family is okay, and I would like to start pointing out that this is the way we will communicate from now on. At least regarding the recitations and the laboratories, I will post these videos each week in my YouTube channel. I had to create one, so I will send you the information on how to access it via email and Blackboard as well. Remember, from now on, communication is going to be essential, so I will need you guys to communicate with me as much as possible with any kind of confusion or question you might have. Just email me, please, or via Piazza as well. Send me or send the other TAs or professors available at that time, at that moment, questions, so we can help you out, guys, because there's no way for us to easily detect whether you have a question or not if you don't speak up. Okay, so having said that, this is gonna be your laboratory number 8, which is chemical equations. This will be the recitation and the laboratory. You guys should have at this point received the information on how to carry on the laboratory report, which is just the information you guys should have recorded or gathered it in the lab session. Of course, as you don't have a lab session, you will get the information and you will just need to interpret it and answer all the questions on regarding the data we send you out. So for this online lab 8, you guys will be using the solubility chart to determine the formation of insoluble salts. So you will need to learn how to determine whether you have a soluble salt or a soluble or an insoluble salt. Sorry. In addition to that, you will be determining the colors of those insoluble salt based on the information you have in the charts. You will be predicting the color of the salts that contain either copper plus 2, or nickel plus 2, because normally these two ions, or cations in this case, tends to form blue or green solutions or precipitates as well. So to keep that in mind, you will be balancing chemical equations, in this case double displacement chemical reactions, which are the most common ones and the ones you will be mostly studying on this lab session, and defining their states of matter, which is just establishing whether that's in aqueous state or solid state if you form an insoluble salt in the end. You will be predicting the outcome of mixing two known salt solutions. So you will be basically taking a look at the solubility chart, and based on the cations or the elements you have in that salt, determining whether that's going to be soluble or insoluble in water, and determining the chemical formula of up to 5 unknown salt solutions. So this is going to be just basically using that exact same solubility chart I just mentioned. At this point, you guys should have noticed that I have mentioned solubility chart plenty of times, and it's because it's very important, not just for this lab session, but for the upcoming exam as well. So start studying how to interpret that chart, not just memorizing the information, because actually we will provide you guys that information on the next exam. You guys will have just to interpret the data, to understand how to read the data you have available in there. Okay, basically what I'm showing you in this chart over here is a double displacement reaction, where before the reaction I have two soluble salts, two aqueous state salts, and once I react them, since in this case I am reacting lead, and normally lead is not soluble, I will be forming a precipitate, which is in this case this very yellow salt you can see in the bottom of that beaker. And this is basically a double displacement reaction. I will go a little bit further and a little bit deeper over that in the upcoming minutes. So hold on. So This is just a little bit of information you guys should know. I just put this for the sake of your knowledge, but I'm pretty sure you guys have seen this before. If not, please take a look at it. These are the topics you guys will be discussing with Dr. Wei in the lectures for this week, and these are the upcoming dates you will be covering. So remember, in this case, I would like to point out that from now on, all reports will be individual. So you guys will be submitting individually your reports. When? Fridays at midnight. Okay, so just pointing that out. Keep in mind that you will need to submit as well your homework number 8, your homework number 9, and in this case, of course, your laboratory number 8. Okay, and this is further information for the upcoming next Friday. Briefly, challenge in this case is writing a full and balanced chemical equation. Why is that? Well, because it's easy when you are dealing with a cation or an anion that has either a +1 or a -1 charge. But what happens when we are dealing that any kind of polyatomic ion that has a different -1 or +1 charge? Then it becomes a little bit harder to understand. So what's going on? For example, I put these 3 reactions, and if you notice in all these reactions, it might be a little bit challenging how to interpret what's going on. So I would just like to point out a few things to consider. For instance, this is a little guide for the students to write full equations in a stepwise manner. So first of all, and I would recommend this just so you can start memorizing the name of each one of the cations and anions you're dealing with, as well as how to name each of the compounds. So sodium sulfate, and I know that in this case, since I'm dealing with this reaction, I can recall that sodium always has a +1 charge because of its family, and sulfate always has a -2 charge. I have barium chloride, which in this case, if I recall, barium, because of the family it pertains to, always has a +2 charge, and chlorine in this case always has a -1 charge because of its family as well. Sodium chloride, actually I should put this so you guys can see that these are the reagents and these are the products. Oops, sorry for that. Okay, so keep going on. I remember that sodium and chlorine always has the same charge, and barium sulfate, barium always has a +2 charge, and sulfate always has a -2 charge. However, if I take a look at the initial formula I'm establishing, I will take a look at how many moles of each one of the elements or ions in this case I have. I have 2 sodiums, I have 1 sulfate, and I recommend you guys to always keep sulfate, nitrate, and any kind of polyatomic ion as the complete polyatomic ion. What I mean is that in this case, for example, do not break this as sulfur and oxygen, because if you do that, it will get a little bit more messy. So I would recommend you guys to see it this way. I have that, I have 1 barium, and I have 2 chlorines, and that's passing to form 1 sodium, 1 chlorine, plus 1 barium, and 1 sulfate. So if you take a look in this case over here, I have 2 sodiums in this side of the reaction, and I just have 1 sodium in this case. What's going on? Something is not working out in here. So this is an unbalanced equation. I always need to balance my equation because that's the way I can preserve mass and I can notice whether my reaction it's okay or it is not okay. So for that, I need to always add coefficients. And what's a coefficient? In this case, the coefficient I'm adding up is this little yellow number 2 I'm adding to my sodium chloride molecule. Now, if you take a look after I add that number 2, now I have, let's go with red. Let me just erase this. Now I have 2 sodiums, 1 sulfate, 1 barium, 2 chlorines, passing to form 2 sodiums, 2 chlorines. Remember that this coefficient is going to apply to the whole molecule. And I have 1 barium and 1 sulfate. And now if I take a look at that, this matches. 1 sulfate with 1 sulfate, that matches as well. 1 barium with 1 barium, that matches too. And 2 chlorines with 2 chlorines. So everything matches. That means that this is correct. Okay, now in addition to that, I can also define the state of matter, but for this I need to use my solubility table, which in this case is this table I am showing you guys over here. So how can I know whether that's right or wrong? Well, let's take a look at that. Let's go with the first compound I have over here. They are telling me that that's aqueous. Let's see if that's true. I have sodium sulfate. If I go to the table, they are telling me that sodium, in this case over here, group 1A and ammonium compounds are soluble, okay? And they are telling me as well, if I take a look here at sulfate, that most sulfates are soluble. These are the exceptions, so keep this in mind. Always read the exceptions. And they are telling me that calcium, strontium, barium, silver, let me see, lead, and mercury in this case are the exceptions. I don't have sodium in any of those, therefore this has to be soluble, and that's the reason why this is aqueous, because it's in solution. Okay, now let's take a look at barium chloride. If I go back in here and I take a look at the chlorine chloride ion in this case, they are telling me that most of the chlorides, bromides, and iodides are soluble, okay? And if I take a look at the exceptions in this case, you will notice that you don't have barium anywhere, okay? Even though barium normally is not soluble, when barium is with chlorine, it is soluble. Therefore, this is in an aqueous state. Now let's go with sodium chloride. It should be easier for you guys to see that as this is, since this is just, like table salt, it will be soluble. But anyways, let's take a look at the table. Sodium, group 1A, and ammonium compounds are soluble. Chlorine, or chloride in this case, most chloride, bromides, and iodides are soluble, and you don't see in this case sodium anywhere. Therefore, this is soluble as well. So, aqueous state. And now it comes the interesting part. Why do I have this soluble, this S in between parentheses in here? Which means that this is solid. And what that means? Well, if we take a look at the reaction we carried on in the end, that means that in the end, after I carried on my reaction, I had one part of my salts in aqueous state. However, in the bottom of my beaker, I got a precipitate. And that precipitate means that this compound over here ended up in a solid state. And that's what this is showing you. So let's take a look at why this happened. Barium sulfate. If we go to the table, we will notice that sulfates in this case, going here, they are telling me that most of the sulfates are soluble. However, if I look in the exceptions, I will find that barium sulfate is not soluble because it's part of the exceptions I have ahead. So I can conclude that this is correct, and barium sulfate should be a solid, not a salt that stays in aqueous state and therefore is not soluble in water. Okay, I hope this example helped. These are a little hints just so you know. copper plus 2 will always form a blue solution, nickel plus 2 will always form a green solution, and sulfur as an anion, in this case any solution with that contains sulfur, will form a black precipitate. Okay, so normally sodium, potassium, and nitrates never form precipitate, which means that will always be soluble in water, and this is basically it. Let me check. Yep, that's basically it. So you have in this case the table. This is the table you guys have in your manual. So this is available in your manual at Blue Door Labs. And actually this is one table I normally use so much because I rather prefer this one, has plenty of more information than the other one. So I normally use this one. You can use the other one as well, it will work. Don't worry about that. I will reference this for the presentation I will upload. So this is a task I have to do, so you can have that reference, but this is one table I have been using since I was an undergrad, and it always helped me big time. So just so you know, guys. Okay, so besides this, I would like to discuss with you, let me just try to find, oopsie daisy, how can I find what I wanted to show you? Okay. 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 And this is the recitation guide. These are here I have a few exercises I would like to discuss with you. Between those, I would like to start with the first one. I will just start pointing to you which exercises I would like to discuss, and actually let me just do this in red color. Oops, let me erase this. As you can notice, I'm not very good dealing with iOS systems. However, I would just like to go really quick over that. I will make the exercises. If you don't understand anything, you can just, like this is recorded, go back and forth. For this, always check the table of solubility I just provided you, or you can just go to your manual and you will find it. So for the first one, barium chlorine, they are asking me here to see what is the expected color I will get for each one of the following solutions. So I just checked on the chart in this case, and for barium chlorine it always will be, why you're not helping me, a colorless solution. Okay, so I guess I will just point out this one in here, and I also would like to discuss this one over here. As I mentioned, as long as you have a nickel plus 2, and this is one of those cases, you guys should be able to right away tell that this is gonna be a green solution. Okay, I hope that's clear. Let's just move on. So this is not helping me. Okay, perfect. Let's just move on. So exercise number 2 and number 3, actually in this regard I will discuss number 2, and you guys will be doing by yourself number 3. So if you combine aqueous silver nitrate with aqueous magnesium sulfate, what's gonna happen? Well, first of all, you have to write down the equation or the reaction you are performing, plus magnesium sulfate. And since this is a double displacement reaction, remember that the cations are gonna change their pairs with each one of the anions. So in this case, silver was with nitrate. That means that silver is gonna exchange with sulfate, and magnesium is gonna exchange with nitrate. So in the end, you should get something like this. Let me see. NO3. However, if you notice in this case, silver always has a +1 charge. That means that, as we know, sulfate always has a -2. This is not matching correctly, so you need to add a 2 with the silver so this matches up. Same case with the nitrate, where you guys need to put a parenthesis surrounding that nitrate and add a 2 so it matches. If there's any question on this regard, please let me know. Okay? Now, there's an extra thing going on in here, and it turns out that this equation is not balanced. So, in order for me to balance this equation, I need to add a coefficient. That coefficient, in this case, let me go with a different color, corresponds to the silver nitrate. If I add that 2 over here, that means that I have 2 silvers in this side, 2 silvers in this side. So let me just, with green, start doing it. 2 silvers over here, 2 silvers over here, 2 nitrates, because remember that these 2 will apply to the whole molecule, so 2 nitrates. Oops. So, oh, this is right. Okay, so 2 nitrates, and this 2 applies just to the nitrate, so this is 2 as well. I have 1 magnesium, I have 1 sulfate, and 1 sulfate. Everything matches up, and now my chemical reaction is balanced. Now, the next question they are asking me is if this reaction produces a precipitate. And in this case, the answer will be yes. If you answer yes to part B, what is the precipitate? Well, then, in this case, the precipitate is gonna be SO4, silver sulfate. Why is that? Because I checked on the solubility chart and I could see the answer. If you cannot see this, if you cannot find the answer to this question, please send me an email so we can discuss this further, or we could also discuss this tomorrow during the recitation. Okay? And if you answer yes to the part B, what is the possible color for that precipitate? And in this case, we will have, oops, no, come on, a white, precipitate. Okay, so moving forward, number 3 is for you guys. Regarding the number 4, it's very easy. It's just to see which ones of these salts you have over here are soluble or insoluble. In this case, they are asking you to check on the insoluble ones. So a little hint over here, you guys should have in the end 7 salts marked. So keep this in mind when you do this exercise over here. And then I would like to just briefly discuss this. On this regard, I will discuss exercises number 6, number 7, number 9. Okay? So, starting from number 6, in this case, I recommend you guys always to start just taking a look at what you have before you start doing anything. So, if I take a look here, before I start, I can notice that I have 6 carbons, 12 hydrogens, and 6 oxygens, and 2 oxygens in here. Okay? And the other side, I have 1 carbon, I have, let's put it together, I have 3 oxygens, and I have 2 hydrogens. That's what I have. Of course, actually, let's make this clearer for you. So we can have in the end 8 oxygens. Okay? If we take a look at that, it's quite obvious that this is not balanced because I don't have the same amount of carbons in each one, in each side of the equation. Same case with hydrogen and same case with oxygen. So this is clearly unbalanced. Now, how can I balance this equation? Well, for that, I need to use, or to add, coefficients. Each one of these spaces over here corresponds to a coefficient. So let's go really briefly into this. I will just put the coefficients so you guys can notice that in this case this is gonna match up. If I add 6 to the O2 molecule in the side of the reactants, I have I have in the side of the products 6 CO2s and 6 molecules of water. This is gonna match up. Let's take a look if that's true. So in the end I will have 6 carbons. Actually, let me use another color for this so you can see it. So in the end I will have, come on, help me out, okay, 6 carbons. I will have in the end 12 hydrogens, and 6 times 2 is 12, plus 6 is gonna be 18 oxygens. And in the other side I will have 6 carbons. I have in here 12 and 6, so 18 oxygens, and I have 12 hydrogens. If we notice, 6 carbons goes with 6 carbons, 12 hydrogens goes with 12 hydrogens, and this is not 180. Let me see, how can I rearrange this? Oh no, that's not what I want to do. I will just put an X in here so you guys can tell the difference. So that's oxygen, and that goes as well. So this is correctly balanced. Okay, so this is the procedure I normally follow up. I will just show you what's gonna be the answer for the following one. In this case, it's actually quite simpler, but I just need to add a 4 in here and a 4 in here. If you notice, I have 1 silicon in this case, 1 silicon in this case. In this case, I have 4 chlorines. In this case, adding this applies to all the molecules, so I have 4 as well. And then you just have to check on the amount of oxygens and hydrogens you have. In these sides, you have 8 hydrogens, and in this case, you have 4 hydrogens in here and 4 in here, equals to 8, so that matches up as well. And 4 oxygens in here, 4 oxygens, and 4 in this side. So this is okay, this is okay as well. And briefly, regarding the other one, I just have to add these coefficients, and this will work correctly. How I did it? Well, following this very same procedure I did for the exercise number 6. So just follow that up, and in the end you will notice that it will work correctly. If you have any questions on that regard, please let me know. Now, they are asking me to mark any combustion reaction from the previous exercise. So how can you tell whether you have a combustion reaction or a double displacement one? Well, remember that when you are dealing with a combustion reaction, in this case, is when you basically are burning any kind of compound. And to burn something, you basically always need to have, where are you? You're here. Okay. Now let's put some color. You always need to add oxygen. Oxygen. So if you add oxygen and you add heat, which is the part they are missing in here, we always put a delta to specify that this is getting heat. This is gonna be a combustion reaction. So as long as you have oxygen and your products are CO2 and water, you have a combustion reaction. So this is a combustion reaction. This one is a combustion reaction as well. And if you check the other ones, none of them accomplish with the specifications I just pointed out, so they are not combustion reactions. In the following one, they are asking me to mark any double displacement reactions. So with a double D. So this is gonna be actually just capital C and capital C. And now let's just mark those double displacement reactions. If you notice, number 8 is gonna be a double displacement reaction. Why is that? Because I'm just changing the order of the anions and the cations, and that very same case applies to number 10. So number 10 is gonna be a double displacement reaction as well. Moving on, and I guess this is the last exercise I will discuss with you, and it's exercise number 13, which is actually kind of interesting. They are showing me a reaction of HCl with sodium hydroxide to form table salt or sodium chloride and water. In this reaction, they are telling me that I have 4 liters of 0.2 molar sodium hydroxide, and they are asking me for how many liters of 2 molar hydrochloric acid I need to add to neutralize that sodium hydroxide. And they are showing me the balanced, and keep this in mind, they are telling me that that is balanced already, reaction, which is this over here. So now let's take a look at that. To start with, they are telling me that sodium hydroxide, I have 0.2 molar and I have 4 liters of that 0.2 molar solution. We need to consider, in this case, consider the proportion or the ratio. Proportion of the reaction. What I mean by that, in this case, they are asking me to compare between sodium hydroxide and hydrochloric acid. How is the ratio between hydrochloric acid and sodium hydroxide? In this case, I can tell right away, because this is a balanced equation already, that this is a 1-to-1 ratio. What that means? That means that, if you recall, if I have 0.2 molar, is the same as saying that I have 0.2 moles per liter. That's right? So if I have 0.2 moles per liter, and they are telling me that in this case I have 4 liters, that means that moles is gonna equal, in this case, molarity times my volume. Therefore, if I have 0.2 moles per liter and I multiply that times 4.0 liters, that is gonna equal 0.8 moles of NaOH. Now I need to use this ratio because this is the way for me to pass from moles of sodium hydroxide to moles of hydrochloric acid. So the proportion, and it's quite simple to see it, is that per each mole of NaOH, I have 1 mole of HCl. Of course, this is not going to change the numerical outcome. However, in the end, I won't be dealing with moles of sodium hydroxide anymore, but I will be dealing with moles of hydrochloric acid. So I have 0.8 moles of HCl. Now, if we recall, using this very same equation over here, if you recall, molarity equals moles over liters. Therefore, liters equals mole over molarity. Therefore, if you recall, the equation is how many liters of 2 molar HCl do I need to add to neutralize that sodium hydroxide. Therefore, this is gonna equal to the 0.8 moles of HCl, I just figured it out, over the 2 moles per liter or molar solution I have. And in the end, this will be 0.4 liters of my HCl solution. I hope this help you guys understand a little bit better what's going on. I would recommend you, before I leave you, to do exercise 15. It's quite interesting, and it will help you out understand better what's going on. And before I leave you, actually, I would like to discuss one extra exercise, which is exercise 18. And after this, we will be done with this recording. So, very briefly, in this case, they are just asking you to determine how many moles of sodium hydroxide are required to neutralize 0.62 moles of nitric acid. And they are showing you in here the equation, the balance equation already. Okay, so you don't have to balance nothing. You just have to once again take a look at the ratio, which in this case is a 1-to-1 ratio. So this is gonna be easy for you to see, because if you can calculate and if you can see, you already have 0.62 moles of nitric acid, and they are asking you for the moles of sodium hydroxide. If I have 0.62 moles of nitric acid, and my proportion is that per each mole of nitric acid I have 1 mole of NaOH, you will notice that the answer has to be the exact same number. Therefore, it should be C. Well, guys, I hope these exercises and this recording help you understand better what's going on. Please remember to feedback me for this, because this is my very first video for any kind of lecturing or recording. So your feedback will help me out very much to, improve this and offer you a better, service on this regard. So have a good one. Please let me know any comments. Email me if you have any questions, and I will send you this information, plus how to access it and any other further comment or, thing I figure it out. Okay? See you guys.